Imagine for a second that you are a speedster. We're talking the Flash from DC or Quicksilver from Marvel.
Maybe even Dash from The Incredibles.
Yeah, exactly. You're moving so fast that the rest of the world just looks like it's paused. To you, the world is slow. You are, well, you're instant.
It's the classic super speed trope. You walk into a room, you rearrange the furniture, and you're gone before a drop of coffee hits the floor.
And for the longest time, that's exactly how I pictured electrons. These tiny, buzzing particles zipping around an atom. I figured if the atom moves, the electron, this little speedster adjusts instantly, no lag.
And you aren't wrong to think that. I mean, physics has operated on that exact assumption for almost 100 years. It's the bedrock of how we model everything.
But today, I have a feeling we're going to break that bedrock.
Oh, we are going to take a jackhammer to it.
I love it when we break physics.
We're unpacking a paper published in the journal Science that completely flips the script on electron speed. It turns out our little atomic speedsters might actually be lagging.
Lagging? Like a bad internet connection in the middle of a game.
That's a very good way to put it, actually. The paper's title is Local Fields Reveal Atomic-Scale Nonadiabatic Carrier Phonon Dynamics.
Okay, nonadiabatic carrier phonon dynamics.
Wow. That is a mouthful. It sounds like something Data from Star Trek would say to confuse Captain Picard.
It is dense, I'll give you that. But the team behind it, led by Sergej Neb from ETH Zurich and Dongbin Shin from the Guangzhou Institute of Science and Technology, they've done something incredible.
What's that?
They basically managed to film an electron tripping over its own feet.
Incredible. Welcome to the Deep Dive Lab, everyone.
Yeah.
Today we are zooming in way in to watch a race between matter and energy, and we're going to find out why the universe's reaction time isn't as instant as we all thought. So set the stage for us. Where is this race happening?
The stage is a very specific, very trendy material called Ti₃C₂Tx.
Ti₃C₂Tx. Catchy. Sounds like Elon Musk's next kid's name.
It does, doesn't it? It's actually a type of material called a MXene, pronounced MXene. MXene. Okay, that's a bit friendlier. What is it?
So it's a two-dimensional material. Imagine a sandwich made of atoms. You have these layers of titanium carbide. That's the meat. And they're all sandwiched together.
Okay.
It's incredibly thin, it's conductive, and on the surface, it has these little chemical groups attached to it, like oxygen or fluorine.
So it's a titanium sandwich with some chemical condiments. Why this particular sandwich?
Because it's a perfect playground for energy. Since it's 2D and conductive, electrons can move through it really freely. But the structure, the lattice of atoms, is also rigid. So it allows researchers to study exactly how the electrons interact with the atoms holding them.
Got it. So we have our stage. Now introduce the rule we're about to break. You mentioned physics assumes electrons are instant.
Right. This is known as the Oppenheimer Approximation.
Oppenheimer, as in the Oppenheimer, the destroyer of worlds guy.
The very same.
Yeah.
Along with Max Born, they came up with this way to simplify quantum mechanics. The logic, it goes like this. Atomic nuclei are massive. They are like elephants. Electrons, on the other hand, are tiny, buzzing gnats, thousands of times lighter.
Elephant and gnat. I'm with you.
So, if the elephant takes a step to the left, the gnat, being super fast and light, is supposed to adjust its position instantaneously. By the time the elephant has finished moving, the gnat has already circled it 1,000,000 times and settled in.
So for all intents and purposes, the gnat is never waiting on the elephant.
Precisely. The assumption is the electron responds instantly to the motion of the atoms. This is called the adiabatic limit.
Right.
It means we can do the math for them separately because the electrons are just always there. They never lag.
It makes sense. If I'm Usain Bolt racing a toddler, I can adjust my speed instantly.
That has been the golden rule. But Neb, Shin, and their team asked a dangerous question. Are we sure?
I feel like in science, whenever someone asks, are we sure, a textbook is about to get rewritten. But here's my skepticism. We are talking about atoms. Things happen in, nanoseconds.
Much faster. Femtoseconds.
Femtoseconds. That's a quadrillionth of a second. If an electron lags by a femtosecond, how on earth do you even see that? You can't just pull out your iPhone and record it in slow-mo.
No, you definitely cannot. To see this, they had to use a mind-bending technique called Attosecond transient absorption spectroscopy, or ADS.
ADS sounds like a villain organization in a spy movie. We messed up! ADS!
It's basically a time machine. Well, a camera that acts like one. Think of it like this. You know, bullet time from The Matrix.
Oh, yeah. Neo leans back. The bullets ripple through the air.
Right. To film that, you need a camera that shoots thousands of frames per second. To film an electron, you need a camera that shoots in attoseconds. An attosecond is to a second what a second is to the age of the universe.
Okay, my brain just melted a little bit. That's an absurdly small slice of time.
It really is.
Yeah.
So here's the setup. They take this MXene material and they hit it with a laser pulse, a pump pulse.
Like a kick.
Exactly, a near-infrared laser kick. And this kick shakes the lattice. It starts the atoms vibrating. In physics, we call these vibrations phonons.
Okay, the elephant starts dancing.
And then they use a second pulse, an extreme ultraviolet pulse, as a probe. This is the flash of the camera. They use this to check where the electrons are while the atoms are dancing.
So kick the atoms, then flash a light to see how the electrons react.
Yes. But here's the really clever part. They aren't just taking a picture of a dot. They're looking for something called local field effects.
Local field effects. Okay, you mentioned this before, and honestly, I got a bit lost. It sounds like when you walk into a party and the vibe is just weird.
That's actually a great place to start. Let's upgrade it to a crowded mosh pit at a concert.
Okay, I'm in the mosh pit, hopefully wearing steel-toed boots.
Now, in standard physics models, we often treat electrons like they're dancing alone in an empty room. It's called the independent particle approximation.
But a mosh pit is definitely not empty.
Not at all. In a material like MXene, the electrons are packed in tight. If one electron tries to move, it pushes on its neighbors. Its neighbors push back. They create these electromagnetic fields around themselves.
So it's the push and pull of the crowd.
Yes, and that is the local field effect. And crucially, this crowd push changes how the material absorbs light. So by measuring those changes, they could track exactly when and where the electrons were moving relative to the atoms. It gave them a timestamp.
Okay, I'm following. They have the super camera, they have the mosh pit detector, they kick the atoms. The assumption is the electrons move instantly. What actually happened?
The electrons missed the beat.
They lag.
They lagged significantly. The data showed that the electrons trailed behind the lattice vibrations by about 32 femtoseconds.
32 femtoseconds. Now, to me, that sounds like nothing. But in this context...
In the quantum world, 32 femtoseconds is an eternity. It's a massive delay. It means the Born-Oppenheimer approximation failed. The behavior was non-adiabatic.
So the gnat didn't keep up with the elephant.
The gnat got left in the dust. The electrons acquired inertia. They couldn't react fast enough to the shaking of the atoms.
Wait, I remember high school physics. Inertia is a property of mass. Heavy things have inertia. That's why a freight train can't stop on a dime. Are you saying these tiny electrons acted like they were heavy?
You hit the nail on the head. In this specific material, because of how the electrons interact with the titanium atoms, they have a large effective mass.
Effective mass. So they aren't actually heavier, they just act heavier.
Think of it like trying to run in a swimming pool. You're the same weight, but the water drags on you. You feel heavy. The lattice of the MXene drags on the electrons in a similar way.
That makes sense. But the study didn't just stop there, did it? I saw something in the notes about holes, and this is where my brain started hurting again.
Yeah. In semiconductor physics, a hole is just the absence of an electron.
Okay.
Imagine a row of chairs in musical chairs. If one person stands up, they leave an empty chair. That empty chair is the hole.
Got it.
Now, if the person next to the empty chair scoots over to fill it, the empty space, the hole, effectively moves in the opposite direction.
Right. The hole moves down the line.
Exactly. So in physics, we treat this moving hole as if it's a particle. And since an electron is negative, the hole acts like a positive charge.
Okay, so we have electrons, which are negative, and holes, which are positive. Two sides of the same coin. You'd think they would behave the same way.
That's what logic would suggest. But logic took a holiday.
What do you mean?
The holes, they didn't lag.
What?
The holes moved almost instantly. The delay for the holes was measured at roughly 7 femtoseconds, which is so small it's within the margin of error for 0.
Hold on. So in the exact same material, the actual particles are slow, but the empty spaces are zipping around like the Flash.
Yes. The holes followed the Born-Oppenheimer rulebook. They were quasi-adiabatic. The electrons were the rebels.
Why? How is nothing faster than something?
It comes back to that effective mass and how they couple to the structure. In MXene, the electrons are just really strongly coupled to the lattice. They're bogged down. The holes, however, interact differently. They don't feel that same drag.
Okay, I need an analogy for this. This is getting abstract.
Let's go back to walking a dog.
Please.
The holes are like a tiny chihuahua on a standard short leash. The parent moves, the chihuahua moves, zip, zip, instant response.
Okay.
The electrons in this material, though, they're like a St. Bernard. And instead of a leash, the St. Bernard is connected to you by a heavy, thick rubber bungee cord.
Okay, that's a very specific mental image.
So you take a step. The bungee cord has to stretch first. It has to build up tension before the dog even moves. There's a delay while that force transfers. Then the dog lurches forward.
And that lurch, that delay while the cord stretches, that's the 32 femtoseconds.
Exactly. That bungee cord effect is what we call strong coupling. And the researchers actually modeled this using the physics of a damped harmonic oscillator.
Oh boy, damped harmonic oscillator.
Is this the part where we talk about pendulums and stuff?
It's the perfect way to visualize it. Imagine you're towing a car with a rope.
Okay, I've done this. It's terrifying.
You're in the front car, that's the atom. You hit the gas. Does the back car, the electron, move instantly? No. First the rope snaps tight, then there's a big jerk, and then it moves.
That jerk is the lag. The researchers actually measured the phase shift of that jerk. They found it was negative 0.4 pi.
Negative 0.4 pi. What does that actually tell us?
Well, think of a full cycle as 2 pi. If they were perfectly in sync, the shift would be 0. A shift of 0.4 pi means the electron is lagging almost a quarter of a full cycle behind the vibration.
Wow. So it's not just a little late, it's significantly out of sync.
Totally. Ideally, you want them dancing the tango. Instead, the electron is doing the Macarena while the atom is doing the waltz.
That is a mess. So here's the big question, the so what question. We proved electrons are laggy in this one material. Why does this matter?
Because this lag governs how energy moves. And even more importantly, it governs heat.
Heat, the great enemy of all electronics.
Exactly. Think about AI data centers. We're building these massive supercomputers to run things like ChatGPT, and they consume the energy of small nations. A huge chunk of that is just managing heat.
Just cooling systems.
Right. Heat in a material is basically just phonons, those atomic vibrations. Electricity is the flow of electrons. The interaction between the two, that coupling, is what generates resistance and waste heat.
So if the electron is rubbing against the lattice because it's out of sync, that creates a sort of friction.
In a sense, yes. Understanding this lag allows us to predict exactly how a material will handle heat. If we know the speed limit, we can design around it. The authors talk about something called crystallographic engineering.
That sounds incredible, like architecture, but with atoms.
It basically is. It means we could design materials atom by atom to control this lag. Maybe we want a material that conducts electricity perfectly but traps heat. Or we want to minimize the lag to make the fastest possible transistor.
So instead of just accepting the materials nature gives us, we can tweak the bungee cord connecting the dog and the walker.
Exactly. We can tighten the leash or loosen it. We're moving from just observing these quantum interactions to potentially controlling them.
And that could mean cooler phones, more efficient AI, maybe even the solar panels that break current records.
It opens the door to all of that. It confirms that we can't just use the simple rules anymore. The instant rule is gone. We have to deal with a messy reality.
I love that. The universe is messy, even at the smallest scale.
Especially at the smallest scale.
So we've covered a lot, from the Matrix to mosh pits to towing cars. If you had to distill this down to, say, 3 key takeaways for everyone listening, what would they be?
All right. Takeaway number 1. The Born-Oppenheimer Approximation. The idea that electrons move instantly is not a law of nature. It's a shortcut. And in some materials, that shortcut just doesn't work. Electrons can and do lag.
The speedster has a delay. Got it.
Takeaway number 2. We now have the technology to actually see it. Using ATS and tracking those local field effects, we can film the dance of electrons with incredible precision.
We have a better camera.
And takeaway number 3. Context is everything. In the same material, holes followed the rules while electrons broke them. It just reminds us that you can't generalize in quantum mechanics. You have to look at the specific conditions.
That's the one that blows my mind. The empty chair is faster than the person sitting in it.
It's a wonderful paradox.
It really is. It makes you think. We rely so heavily on these constants and laws in physics. We build our worldview on them. But this study shows that even the most fundamental rules might just be good enough guesses.
That's the beauty of science, right? Every law is just a placeholder until we build a better camera.
So here's a question for you to chew on as you go about your day. If the fundamental particles of our universe have a reaction time, if they can get out of sync, what other instant laws of physics are just waiting to be debunked? Is gravity truly instant? What about magnetism? What else is lagging that we just haven't noticed yet?
That is the kind of question that leads to Nobel Prizes.
Well, if any of our listeners win one, I expect a shout out. A huge thank you to Sergej Neb, Dongbin Shin, and their entire team for this mind-bending research.
And for giving us a glimpse into the actual speed limit of the universe.
Thank you all for listening to The Deep Dive. If you enjoyed this trip into the atomic mosh pit, go ahead and hit that subscribe button. We have plenty more mysteries to unpack in the lab.
Until next time.
Stay curious.